Not sure about that. So as Brent said, hopefully you guys have already seen what's new in the thermal desktop interface and thermal desktop videos, because today I'm only going to focus on RADCAD. So I'm going to step through the various things we've added with version 6.1. First of all, we've added a new modeling object called an FK locator. And this can be used to define the geometric location of a head loss on a tube, an S-tube, a loss device, or within a pipe. These head losses may be an entrance or an exit loss, perhaps a bend in a pipe, or possibly a loss associated with some type of valve. Historically, losses were assigned to specific paths through the path edit form. If a user needed to define a bend loss on a pipe, they would edit the path closest to the bend and define a loss on that path. However, if the resolution of the pipe was changed at a later date, the loss moved with the path to a new location along the pipe, which may no longer represent the proper location of the bend. Additionally, since there was no graphical representation of the loss itself, the user was unaware that the loss moved to a new location. So by introducing the FK locator, losses now have a graphical representation on the screen, displayed as a yellow ring. In the example here, two losses representing bends on a pipe are shown. These markers are drawn based on the center line of a pipe or based on the path diameter. Note that losses defined on a path in an existing model will not be converted to FK locators. Hence, they will continue not to have any form of graphical display. In many cases, this is fine, but if the loss is in a pipe, we really encourage you to consider changing them to FK locators. When creating an FK locator, you need to define the location of the loss relative to the length of the path or the pipe, specifically the fraction of the total length from the inlet. Locators are associated with a path or a pipe, so if you change the connections for the path or you move a pipe, the locator will move with it. You can also edit an FK locator and change the path or pipe it is associated with. For each FK locator, you can assign a value to the loss, either numerically or using a symbol or expression. Alternatively, you can access the built-in FK calculator to define the loss value. Note that if you have a loss on a path defined through the path edit form, and then you add an FK locator, the FK locator will be an additional loss on the path. In other words, these losses are cumulative or additive. A nice feature of the FK locator is the ability to define a loss as an inlet or exit. When a loss is defined as an inlet, if the flow reverses, the loss will be ignored. Similar for a loss or an exit loss. We have found over many years that many users often ignore entrance and exit effects. So we've added another option here to estimate the vena contracta, the throat area, for an inlet contraction. We've added another modeling object called a T. This is used to provide a user-friendly method to model Ys and Ts associated with merging and diverging flow or in manifolds. So FloCAD has no knowledge whether or not intersecting flow passages represent branched or diverging flow, despite what might be obvious to a user based on the graphical depiction of the drawing. Historically, when modeling such flow passages, the burden was on you to invoke user-callable subroutines to model these losses associated with the Ys and Ts, and to include logic which would modify that logic if the flow reversed. Additionally, FloCAD will attempt to aggregate continuous flow passages into ducts. However, the one-dimensional acceleration equations that are used in duct flow fail to capture the multidimensional effects of a Y or a T. Hence, ducts can overestimate the accelerations and decelerations and do not properly capture the accelerations into a side branch. So the new T object eliminates the need for this complex user-defined logic, and it provides a better estimate of losses than the standard T loss, which is built into the FK calculator. It not only creates the calls to the YT correlation, It also provides a visual indication on the drawing that losses are being accounted for. For example, the orange object shown in this graphic is a T. The new T option also provides support for bullhead connections where the flow comes in and then splits to the left and the right. This is something that we were not previously able to support, but new correlations have been added for this configuration. When creating a T, you must input the ratio of the fillet radius to the diameter of the main run line. You can also define an optional damping for a smoother response and to help solve problematic conversions in steady state. A value of 0 basically indicates no damping, and a value approaching 1 indicates full damping. Note you cannot actually input a value of 1. FloCAD provides 2 built-in correlations, the Gardel and the idle check. The third option uses an average of the two, which is our default selection. In general, the Gardel method is recommended over idle check, but the average is a good place to start for most situations. There are a couple of restrictions to keep in mind when using Ts. First, they are only applicable to 90-degree branches. And second, no 2 Ts can share a path. So you may need to adjust the resolution of your network to space them out such that the Ts are placed on every other lump, as shown here. Note that when placed on a pipe, T locations do not necessarily match your lump locations, and in such cases, the T will connect to the closest lump. Another update with 6.1 is the ability to hold an individual junction or tank as a reference point, essentially making it a plenum for steady state runs, and only steady state runs. It does not apply to transients. This is useful when modeling certain types of two-phase fluid systems or for systems where the focus is on filling or emptying a tank. You've always had the ability to create user logic to create a hold lump on and later release that lump, but we've added an option directly on the lump edit form. When you select this option, FloCAD will automatically include a hold lump call for steady states and then release that hold for transient runs. This replaces the need for the user-defined logic. We've also included a similar option in the case set manager. However, with this option, it will hold all lumps for a case. This is useful when you need to hold an entire fluid submodel constant or entire fluid model constant while you initialize the thermal models. There's a similar option to hold all thermal nodes in the boundary state. I believe that was also added in version 6.1. We made a bunch of expansions on pipes. So I'm going to try to walk you through some of these. Some of them get pretty complex. So a lot of it is just a reorganization of the form. For example, if I go and I select a pipe with what used to be called a pipe with wall is now a pipe with outer wall only. When this is selected, options for the outer wall can be selected, such as the specific cross-section, cross-section with no nodes generated, which is the equivalent to the old option pipe without a wall option. And there is still an option to use surfaces to define the wall. Nothing really new here, just rearranging of the form. New for 6.1 is the ability to add inner walls for pipes. This feature not only supports modeling of annular flow, but it allows you to define complex geometry inside pipes. When the pipe with an inner and outer wall option is selected, it will give you the same outer wall options as before, but it will also activate new options to define the inner wall. This inner wall can be one or more surfaces, or it can be a blocked volume. With this feature, you can model concentric pipes, nesting multiple pipes if necessary. When using surfaces as walls, FloCAD will shoot rays from the pipe's center line to determine the cross-sectional area of the pipe. This feature supports the ability to define fairly complex inner wall geometry. However, sometimes it can lead to problems. basically when shooting rays to calculate the flow area, you can end up with slight numerical errors, which appear as slight expansions or contractions along the pipe, causing havoc to the solution process. To prevent this, we added a new averaging feature. Whenever you have complex geometry in the pipe, but essentially a constant flow area along the length of the pipe, we recommend this option be activated. When using a surface for the inner wall, the wall surface dialog in the lower right of the form, and I'm going to just sort of jump back here to the full form. So the lower right corner is where this wall surface ID dialog is. Anyways, here you can see I have set the outer surface of pipe 2 as the inner wall for the pipe I'm currently creating. Basically this is creating, it's the pipe I'm currently editing, and it's creating concentric pipes. So the volume defined by this inner surface is going to be basically displacing flow and changing the flow areas in my pipe. It'll be changing hydraulic diameters, etc. And all of this will be taken into account by FloCAD. So there's no user intervention to modify hydraulic diameters or heat transfer tie path fractions. By default, FloCAD will create additional heat transfer ties to this inner surface between the fluid and the inner wall, basically. This is disabled by unchecking the generate tie option. When ties are created, path fractions for the heat transfer will automatically be determined by the code and applied to both the inner and the outer ties. Another new option is the ability to specify there is an enclosed surface for heat transfer. This could represent additional supports in a pipe or fins on the interior surface of the pipe, possibly an object in the flow stream. So you can use the Add Tab button to create additional heat transfer ties as needed. Also new is the ability to specify a blocked area along the length of the pipe. Both of these features will adjust the flow area, the volumes and such. And last, we have a new option to account for wall elasticity, which uses Young's modulus and Poisson's ratio in the thermophysical properties. This feature supports modeling fast pressure transients such as water hammer. Previously, we had a similar option in Logic Manager, but it applied the elasticity globally to the entire model, whereas this new feature provides control at the pipe level. And I want to point out that these new abilities to define inner walls and closed surfaces and blocked areas is sort of confusing to start with, but they're very powerful. So I want to quickly show you a few things that you can do with these. So here's an example of an object enclosed inside a pipe. In this situation, the heat transfer between the fluid and the object can be modeled. Since this is not annular flow, the pipe type is set to a pipe with an outer wall only. And then using the wall surface ID dialog, excuse me, I just need to get a drink of water here. So using this wall surface ID dialog, an enclosed surface for the tie has been selected and the surface is defined. In this example, the surface is all 5 sides of that brick. To create the heat transfer tie, the option to generate a heat transfer tie on the brick has to be checked. Note that since this is not annular flow, the object will not be displacing any volume in the fluid flow, nor will it have any effect on the flow itself through the pipe, other than adding heat transfer from the object to the fluid. Here's another example that has a blocked area that runs the entire length of the pipe. In the graphic shown here, the gray bar is for visualization only, and it represents the blocked area. So it's not actually an object in TD, it's just here for graphical purposes. So in this example, heat transfer to this blocked area is not of any concern, but I want to model the displacement of the area, the displaced volume, and adjust the hydraulic diameter and the flow areas properly. So in this case, the pipe is set to be annular using the blocked area option for the inner wall. And then we select the blocked area. When you select the blocked area option, it activates a new dialog on the Pipe Attributes tab where the blocked area can be defined. And here I've input a cross-sectional area and a hydraulic diameter. If this were a circular area, I would simply only need to put, I could just put in the diameter. I think I still need to put 0 in for the blocked area. But it basically assumes circular if there's a 0 blocked input for the area field. It assumes circular. Okay. Another option that you can do with these new features is creating concentric pipes. Basically, we're taking it a step further. So we can define the annular flow using another pipe as the inner surface. So here is a pipe that has been set as a pipe with inner and outer walls, and the inner wall has been set to be a surface. Then using the wall surface dialog, the inner wall selection has been made, and I'm basically selecting the outside of another pipe. So when creating concentric pipes like this, FloCAD will automatically account for the volume displacement caused by the inner pipe and adjust the hydraulic diameter automatically. It'll also adjust path fractions for both ties based on the total wetted perimeter for that flow area. And using this method, you can keep nesting these things so you can have a whole series of nested concentric pipes. So hopefully you're starting to see some of the numerous applications for these pipe features. Remember, you can add as many ties as you want to any single pipe. The ability to create ties to multiple inner wall surfaces allows you to tailor heat transfer around the circumference or along the length of the pipe, perhaps due to fouling. The ability to create multiple ties to enclosed surfaces can support complex geometry in the pipes. We've also changed how pipes are connected. Oopsie, I skipped something here. Let me go back. Oh, there it is. So we've added new user callable routines to support rectangular ducts and concentric annular circular ducts. These routines will calculate the hydraulic and effective diameters along with variations of the laminar Nusselt number based on the geometry of the duct. So subroutine and duct is designed to be used with concentric pipes. Note that these have to be circular for this routine. And the subroutine rect duct can be used for rectangular ducts. Both of these routines should only be called once per run or per unique passage, and we recommend only calling them in the operations block. We've made changes on how to connect pipes. Historically, we had a connect option for pipes that essentially went through and it merged the end lumps and the end nodes, effectively making one continuous pipe or duct. There were several issues with this method. One of the most crippling was that once connected, you could not change the subdivision of a pipe without disconnecting it first. The new method supports using pipes for the fluid connection. Using ports for the fluid connection between pipes while still merging end nodes. Since we introduced ports in version 5.8, we have found that they provide a much cleaner option for connecting pipes while retaining the ability to change the subdivision of a pipe without having to disconnect pipes. Older models, which use the merge option, are still supported, but when you open such models in 6.1, you will be given a one-time opportunity to convert to the new method. However, any new pipe connections you create in 6.1 will only use the new method. Since we also introduced T's with version 6.1, with version 6.1, you now have the option to convert a port-based pipe connection to a T, allowing you to account for the losses in merging and diverging flow. Earlier, I mentioned a new wall elasticity option. This came about through expansions that we made in the area of compliance factors. We've separated compliances based on the various causes. So these causes are basically trapped gases, safety factors, and so forth. Fluid compressibility, which is set by CompLic in the logic manager and applies to the entire model. And wall elasticity, which can now vary from pipe to pipe. These three components will now make up the total compliance of a lump. Compliances can also be set for vessels or compartments, and you can override pipe level compliance at using the lump edit form. We've made some changes in compartments. The key feature here now is the ability to create subtracted volumes in a compartment. So you can now define interior solids, which create the overall compartment, and then specify solids that represent displaced volumes to be subtracted. This process is often much easier and faster than trying to create a single complex mesh of the fluid volume. It also helps with isolating stagnant liquid cores when modeling pressurization of tanks. So basically, you can define a simple mesh for the entire volume and then create simple meshes of the volumes to be subtracted. For example, when modeling an aircraft fuel system, you can subtract out the volume of the hydraulic components inside the tanks. We've also modified compartments to make wall surfaces optional. Previously, walls were required, so if you were modeling an adiabatic vessel, you would have to disable the wall mesh within Thermal Desktop, which was a bit cumbersome. This allows the creation of adiabatic compartments when you are not interested in modeling the heat transfer to walls. If you do not define surfaces for walls, the earn radiation option is no longer applicable, isn't applicable for those where you don't have surfaces for walls. So if you've if you've not put any surfaces down here in your walls, this option to use the radiation in the enclosure becomes grayed out. We also have a few minor updates with 6.1. The first is supporting new pressure units. So to support inputting Young's modulus for wall elasticity, we added MPSI and gigapascals, since Young's modulus is usually defined in these units. And while we were at it, making these changes, we also added the ability to define pressure as PSIG to support gauge pressure. So if this is selected, FloCAD will automatically set P-atmos, the atmospheric pressure, to be minus 14.696. So it takes care of that for you automatically. We've also changed the default value of MCH, which specifies the method to use for choking calculations. The change takes the MCH value from Versick's non-equilibrium value of -2 to Dyer's method, which is -3. We made this change because it provides better results for two-phase throats and constrictions. This is especially relevant for flow constrictions at inlets and it supports the new FK calculator throat options. Note that this change only applies to tubes, S-tubes, and lost type paths. Orifices, reducers, expanders were already set to Dyer's method, and other path types have not been changed. They remain the same. I do want to point out that when you open an older model in version 6.1, you will be given the option to automatically change your model to these new values. This prompt will only occur once per model file. And last, I just want to point out, as part of an ongoing internal project we've been working on to revamp our user manuals, we've removed all the step-by-step tutorials from the user manuals. So the tutorials can now be found on the new tutorial forum in our community forum at the website. This location will allow you to ask questions related to each tutorial. It will also allow us to update and add new tutorials as needed without having the process linked to our normal product release cycle like it has been in the past. With this change, we've added tags and such to the tutorials so that they can now be found through our tips and samples search page on the website. So if you go in and you type something like, vapor compression, it's going to not only show you sample models and other information, it will also go through tutorials if we had a tutorial that was relevant to vapor compression, which I don't think we do. I'm not sure why I said vapor compression. And that's it. That's our presentation for today.
Thank you very much, Jane. Just a reminder to everyone that there are two ways to ask a question here. You can type a question into the question panel at probably near the bottom of your GoToWebinar control screen, or you can raise your electronic hand if you would like us to unmute you so you can ask your question over the phone or microphone. Here's one, Jane. Can tees handle flow reversals?
Yes, that's taken care of automatically. I do want to point out that in some transients with compressible fluids, you can still get into situations where the underlying correlations that the underlying correlations can't handle, but those are rare. You can disable any warnings or aborts if the illegal situation isn't perpetual.
Okay, hopefully that answered the question. If not, please ask it again. Another one is, where are there samples or tutorials for FK locators and tees?
So part of the 6.1 release, we went through and tried to update the majority of the sample problems that we have on our website. So most, if not all, those have been reworked, and many of them now include FK locators, since we found them to be so much more convenient than the old methods where the FK is hidden underneath each path. So especially any samples where we had inlets and outlets where you might want to apply constrictions to catch choking, those have all been updated. So for tees, those aren't as common. There are a couple places where we have used them. There is a new validation case for manifolds that gives tees and FK locators a good workout. There is also a sample model for methods of optimization, which has been updated to use tees. And again, if you come back to this tips and samples page shown here, most of these, I believe, have been tagged. So if you type in FK locator, you should be able to find some samples or tees.
Thank you. Let's see, someone asked, can you have a 4-way tee on the question panel? And the answer is no, unfortunately. Right now, just 3-way tees. I suppose you can put two 3-way tees together, but that's not a satisfactory answer. Sorry about that. Also another question, Jane, what happens when you move one of the new types of connected pipes?
Actually, Brent, I'm going to let you answer that one because you've done a lot more testing on that than I have.
Okay. Yeah, there were a couple reasons why the old connection method was not satisfactory. One, as Jane mentioned, was that you can't change the subdivision. It was kind of a welding mathematically. Whereas the new connection is more like an electronic brush or something. It's more of touching, and part of this was enabled by ports, which allowed us to just point to something rather than to connect to it. So the connection is only made when you actually run the model. So if you move a side connection up and down a pipe, it'll automatically reconnect to wherever you are moving the side pipe to the nearest lump. And that was one of the big reasons for changing the way connected pipes work. You may have to remerge nodes if you do that because you've broken the thermal connections, but usually those are pretty minor compared to advection. And I guess I should also mention that tees kind of work the same way. The tees actually are port-like, and so if you slide them up and down a pipe, it'll automatically reconnect to the nearest point too. Hopefully that answered that question. Here's one on pipe wall elasticity. Can it be used for water hammer? Can you do thick-walled square pipes?
Okay, two-parter. So regarding the water hammer, yes, it is intended for both water hammer and for general compliance. If an infinitely stiff wall is unrealistic or creates pressure errors. For the second part regarding the thick-walled or square pipes, yes, it can handle thick-walled and rectangular channels. It assumes they are rigidly supported along the entire length. The Syndafluent manual shows the formulas.
Thank you. And it looks like one more is about how do you handle heat transfer? What correlations for enclosed pipe objects?
For enclosed objects that don't run the whole length of the pipe, you can make your own correlation, or you can choose from one of the built-in external, there's built-in correlations in the tie form, and you can choose one of the external options. Just remember that from the object's perspective, the internal flow of the pipe is external to the object, so it's going to be basically an external flow to the object. For internal pipes like angular flow or other objects that go the whole length of the pipe, the program is using a wetted perimeter and flow area and then treating the internal wall like the outside wall. I don't know if that made sense or not.
Yeah, I was thinking that, the idea of an internal object is kind of an interesting one that, a lot of times the idea of an internal wall, whether it's an annular pipe or concentric pipes or something, probably isn't too confusing, but the idea of an enclosed object might surprise people a little bit. And I was thinking maybe the best way to think of that is like a wind tunnel. What if your focus was not on the wind tunnel itself, but on the object you're putting inside the wind tunnel? That's, of course, not the only application for it, but gives you a way to think about it. And, it's the same sort of thing in a compartment, where a compartment can have internal objects that may be a wall, and they may just be something floating around or internal. And if that's true, it would use completely different heat transfer than you might assign to an actual wall of the pipe or compartment. So hopefully that helped more than it confused. Any other questions here before we close? Well, thank you. I don't see any more coming in.